Hello, everyone. We're going to show some of the work we've been doing through this Oceanhackweek in this project that is a spatio-temporal mapping of Argo data. So here are the hackers that participated and the mentors. So to briefly summarize what we were trying to do, we were trying to map the Argo data using a Gaussian process regression in order to model the anomaly fields from the measured data. So here you can see an example. We are basically adapting the paper made by Kusila and Stein. I'm sorry if I'm not pronouncing that name right. They did this with the Argo raw data for the global ocean. You can see here the example of the Argo raw data and the predictions. So we use a suite of open source open source tools. For the statistical thing, for the process, we use George. It includes a Gaussian progress regression module. Then we use ArgoPy for the ingest of data. So here is like a brief explanation of the steps that we had. Also, this project in the main GitHub repo, there is a binder button where you can launch your own binder session and tweak any setting that you want. So first we load a subset of Argo data using ArgoPy. So I gotta say that the API of ArgoPy to load this data is really easy. We didn't have to download anything. Then we have to interpolate the data onto a common pressure level. To keep things simple, we are just using one pressure level, and this is where we are going to do all the mapping. Then we have to compute the mean state by using a least square fit and with a few basis functions. I'm going to go through this in a moment, and seasonal harmonics in time. And subtract the mean in order to get anomalies, and then these anomalies are the ones who go into the Gaussian process. So well, here's a bit of code, the bounding box of the data, the time, initial day, final date. Here are some of the functions that we defined to the harmonics, build the basis functions, and find the mean state. So how do we do this? In order to find the mean state, we fit in space to a two-dimensional polynomial regression and in time in harmonics. For this example, we are using just two harmonics in time. So here we do the fitting. Once we get the fitting is basically solving this linear algebra problem where we have A is the matrix with all our basis vectors. X are the parameters that we are trying to estimate, and B is the mean state and anomalies. So after we compute the mean state, we can nicely subtract this, all thanks to XRA and the coordinate system that they have. Well, here's a nice plot of the location of the study that we are showing here. You can see here the mean state that we compute, that we fit, and the subtraction that this is the anomaly field. So this is a plot in order to explore, if I'm not wrong, the seasonality of our data. Well, now we move to the Gaussian process regression. So I think I was...
Yeah, thanks, Gerardo.
Okay.
I'll just cover quickly the Gaussian process regression part. So we used George, which has a really accessible Gaussian process regression module. And it requires input coordinates of, well, it can perform a Gaussian process regression on in d dimensions, but we use 3 dimensions here, the latitude, longitude, and time axis, which we have pulled from the Argo data, and then the temperature anomalies. So to initialize the Gaussian process, we estimate length scales based on some understanding of the system, and then put these length scales into a kernel or a covariance function, which kind of describes the autocorrelation of temperature the spatial distribution of the temperature. Then we initialize the Gaussian process, which is then code 42, and compute a first kind of estimate. And we include observational error. We use some test grid points for the prediction, and predict the interpolation. And then the figure in 46 shows the prediction versus the original data. So this is our first iteration. We then improve the prediction by zoning in on the parameters using maximum likelihood estimate, which minimizes the negative log likelihood to improve our length scales and parameters in the covariance function, which after optimizing, we rerun the prediction, and the next figure shows a improved distribution or interpolation. So in the first panel on the left is the prediction, and then the prediction with the maximum likelihood estimation, and then the truth on the right and the scatter plot. And you can kind of see, if you squint your eyes, that the maximum likelihood estimation is improved compared to the scatter plot. But I think, future work we will, there are a number of different kernels you can define, and future work would work to improve this method. And what's cool about this method is we interpolating both in space and time, so you can also get an idea of time variance, the time series, which we have shown here, not very clearly, but the plot at the bottom here shows the time varying in, the x-axis is days since a reference point, but nevertheless, at some point in the data set, you get this time series with some variance, which seems to estimate the truth pretty well. So this is, first attempt, and we have future plans to improve on the functions and create a wrapper function so that we can upscale, so it's a usable function, and work on making the function upscalable. So this is a very small window, so we need to add to it, so you can have maybe a moving window or some